Alright, this is the chapter 14 video for strength of materials. We're going to be looking at how to find stresses in beams. So first of all, let's take a look at a simply supported beam. I'm going to draw a roller support. I'm going to draw a beam that has some height to it and a pin support. This is what's called a simply supported beam. This is the most common type of support condition for a beam, with a pin and roller at either ends of the span. And if we were to apply a load to it, let's just say a simply supported or a concentrated load in its midspan, the beam would deflect. So I'm going to change my pen color here and draw in an exaggerated fashion the bending that would occur with a dotted line here. So what happens when the beam bends like this is that if we were to draw vertical parallel lines on the original beam, those lines bend outward with the bending of the beam. The amount that these lines spread apart at their base is more than it is at the top. So what's happening is the bottom of the beam is being pulled apart in tension, and the top of the beam is being pushed together in compression. So if we were actually to look at this beam, so I'll draw the beam here again with the roller support, and we're just going to kind of cut it off right there. If we were to look at the stresses occurring in this beam, what's happening is at the bottom of the beam, it's in extreme tension. And as we go higher up the cross-section of the beam, that tension gets less and less and less until we reach what's called the neutral axis of the beam, where there is no stress. So this is an invisible plane going through the center of the beam where there's neither compression nor tension stress. And then above the neutral axis, the stress is going to increase, but then it's going to be in compression. So we're seeing the maximum amount of compression at the top, and then that compression value decreases until we hit the neutral axis. Below that, the stress begins to increase, and we see more and more tension. So the maximum amount of stress occurs at both the very bottom and at the very top, and we refer to these extreme top and bottom of the beam as the extreme fiber. So think of it as like the skin along the very top and bottom of the beam. Those are the parts of the beam that experience the most amount of bending stress due to compression and tension. So when we talk about bending stress, we're actually talking about a combination of these stresses, both compression and tension. But we can calculate what the stress is in a beam. We're going to use the letter F to represent stress with a subscript of B for bending. So bending stress is equal to MC over I. So what are M and C and I? First of all, M is the bending moment. So we just learned how to make shear and moment diagrams. Part of the reason for that is so that we can know what the moment is in the beam at any given point along its length. Typically, we're only concerned with the maximum amount of moment. C is simply the distance from the neutral axis to the extreme fiber. So we're going to start off just looking at beams with rectangular cross-sections. And so the neutral axis in that case is going to be in the geometric center. So whatever the depth of the beam is, the neutral axis will be located at d over 2, d over 2, and the total depth of the beam is d. We tend to use d to describe depth of a steel beam at least. And then we have I. I is the moment of inertia. And again, at least initially, we're going to be looking at rectangular cross-sections. And so I for a rectangle is equal to 1/12 base times height. So we're using height here in place of depth. So 1/12 b times h, 1/12 base times height. I'm sorry, 1/12, not 1/2. 1/12 base times height is how we calculate I for a rectangle. For other shapes, like wide flange sections, we could theoretically calculate what the I value is for a shape like this, but we don't really want to do that. Instead, we want to see the appendix. And for wide flange shapes, that's in Appendix A. The moment of inertia can be found. The moment of inertia can be with respect to the x-axis, which is what we're primarily interested in when it comes to bending about the primary axis. For bending from side to side, the shape would bend about its y-axis. So there is an I sub y, but that's typically not what we're interested in when we're looking at beams. We're more concerned with the I sub x. So again, for a simple shape like a rectangle, we can calculate that ourselves. For another simple shape like a circle, or maybe a triangle, that's something that we could look up the formula for in the back of the book. And for shapes like hot rolled steel shapes, such as wide flanges, we just want to look that up. We don't want to have to calculate the value ourselves. We just want to look it up. So if I scroll down here to give us a little bit more room to work with, and I rewrite that formula for stress, bending stress, F sub B equals mc over I. What engineers have found is that it's more convenient, rather than using I and C separately, to replace the two of them with one single variable called the section modulus. So just like a moment of inertia, section modulus can be about the x or y axis. We are going to be concerned with the section modulus about the x axis. So this is I sub x, this is S sub x. And the section modulus is equal to the moment of inertia about the x-axis divided by c. So in other words, this equation here for bending stress becomes F sub b equals the moment, whatever that happens to be, divided by the section modulus, S sub x. Now, as design engineers, we typically are given some allowable stress, and what we want to know is how big does the beam need to be in order that that allowable stress is not exceeded. So in other words, we just want to rearrange this equation for the section modulus. S sub x is equal to moment divided by, and when we're given an allowable stress, we tend to use a capital F for that because it's a fixed amount. F could be B to indicate we're still talking about bending stress, and then maybe followed by, in parentheses, allowable, or just allow. So whatever the moment is divided by the allowable stress gives us the required section modulus. Remember units. This is the most common thing I see beginner students get incorrect. The stress is typically going to be in PSI, pounds per square inch, or KSI, kips per square inch. Therefore, in order for the units to cancel out, the moment has to be in either pound inches or pound, I'm sorry, not pound, but kip inches. In other words, not pound feet or kip feet. So that's oftentimes a more convenient unit to describe moment in because the span length is typically given in feet. But if we were to use feet, it would not agree with the inches in the allowable stress and therefore would throw off our answer. So we need to make sure we're using consistent units. And those units are typically, at least when we're using the English system, going to be inches. All right, let's look at one quick little example here before we wrap up this video. If you look at example 14-1 in the textbook, we are given a timber beam, and if we look at the cross-section of this beam, it has a width B of 7.5 inches and a height H of 11.5 inches. So, as I said earlier, typically with steel sections, we refer to the depth D. With other materials, such as timber in this case, or concrete, we do tend to use H for height. So it's rectangular in shape, which means the neutral axis is going to be at the geometric center. The top and bottom are symmetrical about this axis. And so C, the value of C, is just going to be equal to half that height. So we could say C from the neutral axis to the top is 11.5 divided by 2. And so that is equal to 5.75. But we could also measure C from the top to the bottom. And again, that's still going to be 5.75. So for shapes that are symmetrical about the horizontal axis, it doesn't matter if we're talking about the top or the bottom. This will be a topic of conversation at a later time, but when we have a cross-sectional shape like this, like a T shape, we're going to have two different C values. We're going to have a C value for the top and a C value for the bottom. They're not the same if the shape is not symmetrical. Actually, this should be bottom. Not the same if they're not symmetrical about the x-axis. So what do we want to know here in this problem? We want to know what the section modulus is. What is S sub x equal to? Well, S sub x is equal to the moment of inertia divided by C. What is the moment of inertia equal to? Moment of inertia for a rectangle is equal to 1/12 times the base of 7.5 times the height of 11.5 to the third power, 1/12 bh cubed. And so that, if we calculate that out, is equal to 951 inches to the fourth power. And we've already determined C to be 5.75. That's inches. And so the section modulus, S sub x, is equal to 951 inches to the fourth divided by 5.75 inches. And so 951 divided by 5.75 is 165.4. And therefore the units for section modulus is going to be inches to the third power. Okay. In the next video, we'll look at how we can use this section modulus.